Good morning. So we are continuing our discussions on PLA, the folding technique for minimizing a PLA structure, as I told you. So I started with an example in the last class. Remember that I asked you, or rather we are thinking of realizing 6 output functions out of 5 input variables and consisting of 8 independent product terms. That was what we started with. And we had shown the regular PLA structure for this, for realizing the same output functions. The drawback of the regular PLA structure, as I told you, that it takes large area. So as a result of which, you know that the packing density is affected, speed is also affected. Both the power consumption increases. So the regular PLA therefore is not a very desirable one. We have to do something so that we can minimize the PLA structure. We can achieve the same functions with smaller chip, and for that we propose the folding of PLAs. The first folding proposal, as I think I mentioned earlier, that you can, there are 2 planes in a PLA. One is a AND plane, the other is OR plane. In the AND plane, there are inputs which we called columns, and there are outputs which produce the product terms, and we call them rows. And it is possible to split the rows so that from 8 rows, it may be possible to convert to get 4 rows. So there is a possibility of reduction by splitting rows called row folding of the AND plane. I am speaking of the AND plane. So it is also possible to fold the columns of the AND plane. We shall see. So we shall give you some example where the columns can also be split for the AND plane. Exactly the same discussion is valid for the OR. That means we can do various things. We can fold the rows and columns of AND plane and or OR plane for achieving the main target, that is the compaction of PLA. In the last class, we are considering simply the row folding of the AND plane of the PLA, the same PLA which we first, of which we have shown the regular structure first, for which we have shown the regular structure. Where is the regular structure? Sorry, these are the regular structure. And then we first told that we shall try to minimize this PLA by row folding of the AND plane. What I did, you remember, that we write the product terms in order of priority from A to E, and we got things like this. And then just divide into 2 groups, one consisting of A, AB bar, this one and this one. The other half is this one, this one, this one and this one. Then I say that I will have the first row split into 2. One row will produce A, one half will produce A bar, the other half will produce C bar. One half directed towards the left in my layout, in my circuit diagram, will produce A bar, the other half will produce C bar D, and so on and so forth for the second, third and fourth rows. You note that all C, D, E kind of terms are in the right hand side, all AB and one D term I could not avoid because there is ABC are also placed in the left half. Okay? And we also, you remember, as a result of this, because we are having the split of rows, I have to place the OR planes in both sides. I cannot manage by a single OR plane on one side of the AND plane. I have to keep the OR planes on both sides. And therefore, I have to see that out of these products, which output functions depend mostly on ABC and mostly on CD, etc. And that was categorized. We found that Z1, Z2, Z3 are independent of AB, so I can put them to the right hand side, whereas the other variables, other output functions, they are independent of A, I can put them all in the left hand side. That was the methodology we were following in the last class. And after, at the end, we came to a structure which is like this. We completed the drawing of the only the rows of the AND plane. So these are the AND plane. And plane row folding. And what was the methodology you have seen that? I told you that I will produce the output functions A bar, AB bar, A bar, B bar, C, and A, B, C, D bar at the left. And the remaining functions dependent on C and D and E to the right. So to produce A bar, how to, but I first drew it, but what was the methodology of independent drawing? So I want to get A bar. So what I want to do, I should invert A. Because basically there is a transistor which inverts or produces NOR function. So I should just put a dot here, and then it is not necessary to extend this line to the right hand side, because it is not necessary. I can have the pull-up transistor or the load transistor either here, any point at the right of this dot. Am I correct? Please see that. I am getting A bar here. So this is the dot which produces that A bar function. Is it necessary to extend this line to the right? It is not necessary. I can split anywhere, wherever convenient for me. I have just split here. Then there is no space for me to keep the transistor at this side, because this is my problem. I have to keep OR planes on either side. Therefore, I have to make some metallization routing so that the transistor is kept on the top side. So this is the load transistor for this inverter. There is an inverter, is it not? This inverter. Then this function produces C bar D. That means the D bar should be connected. So this should be a transistor should be located in this line. So I start drawing a line from the right hand side towards the left. First I reach here where I need a transistor to apply D bar at the input. Then I go further left at this point, and I have to apply C at the input so that I get the NOR function C bar D, so that ultimately the product is we get C bar D. You remember that? And there is no need to go further to the left. I can go up now. But because these two transistors are matched pair, normally they should be very clear. It is not necessary. It is not necessary that they should be kept like this. But for the convenience of showing the transistor, what I have done, I have just routed the wire upward like this from the left as well as from the right, and I have shown the two transistors as if something like a matched pair. It is not necessary. All there is no need of a matched pair kind of requirement in MOS technology, because this is not differential pair. Please remember. But I have shown so that it is normally the way circuits are drawn. So I have drawn. Similarly, you just see A B bar what I have done. So for practical purpose, therefore, what I have to, you start from the left, draw a line. Then come here, because you have to apply now A bar at the input. So there is a dot here. Then B at the input. There must be a dot, and there is no need to go to the extremely to the right. You can terminate anywhere and go up. You can go up from anywhere to the right, from the right of this point. Similarly, from C, you do the same thing, and you find you have to finish here. Then go up. You are now putting the two transistors close. It is not, again I am telling, there is no need to show that these two transistors should be closed like this. Okay? And you have shown. Exactly in the same way, I have drawn the other lines. So what was the approach? First I grouped the product terms in order of priority from the first variable to the last variable. Then group them into two halves, classify them into two halves. One half is dedicated for the left plane, left OR plane. The other half is dedicated for the right OR plane. And then you start from one side, go on dotting, and whenever you have finished this thing, you go up. Exactly that way, this way. And you can see that, though while drawing I did not follow that approach, but exactly when you have to draw it, you have to follow that particular approach. So now the AND plane is over. Now you have to show the OR planes. Now while showing the OR planes, you see that, as I told you, in this right hand side, what are the functions to be created? You just see naturally Z1, Z2 and Z3. These are these functions, these products are involved here. Z1, Z2 and Z3. Whereas Z4, Z5, Z6, whatever the products necessary, they are available in the left hand side. You just see. These are all available here. Whereas for Z1, Z2, Z3, whatever products necessary, they are available in the right hand side. So you just have Z1, Z2, Z3 implemented this side, and now again you can make some folding of the OR plane. It is not necessary to draw 3 lines for producing. You can do it, but that will again we shall try to make some space, save some space here also. So what I will do, again here also I will try to fold the lines. In what way? You just see that, for example, you note that Z1 and Z2. What is Z1? Z1 is D plus E bar, and Z3 is C plus C bar D. D plus E bar is available here, and C plus C D bar is available here. Okay? So I can split the so-called column. Actually, it is a row of the OR plane. Please remember, the columns are actually the rows of the. So you can split the column here to produce Z1 and Z3, Z2 functions. So what you do simply, you see that Z1 is equal to DE plus E bar. So DE plus E bar, and you get Z1 here at this point. All right, and naturally it will, this is the load transistor for the particular one. I have to show to, I have to extend to the right. All right. Then what about Z2? C plus C bar D. So I just do this thing. And I here. You get Z2 here. So you see that column is folded. Actually, again, let me tell you, this is again called row folding. Basically, these are rows of the OR plane. And then the other function is Z3. Z3 has to be managed by single thing. You can keep it either this side or that side, is up to you. And Z3 is C plus C bar D plus E bar. So C plus C bar D plus E bar. So in the right hand side, right hand OR plane, this is the OR plane, right hand side. I produce the functions Z1, Z2 and Z3. There has been a folding, and therefore there is a space, saving of space. Okay. Then in the left hand side, if you just check that I want to produce AB, so naturally Z4, Z5 and Z6. This ABC D bar and A bar B bar C, these are available here. So what I can do simply, I can produce a function like this. Here I get Z4. and this is Z4 means A, B, C, D bar, and A bar, B bar, C. And of course, we have to have my transistor here. And then you are getting Z5, which is A bar and AB bar, which are available on the top side. So what I simply do the following. Here I have not shown this one. This has to be shown. Please see. I did not show that. And finally, Z6 is this one. And for Z6, you see A bar, B bar, C, and A, B, C bar. A bar, B bar, C, and A, B, C, D bar. And again, I have to show my transistor. So carefully see what I have done on the right hand side. I have produced the three functions Z1, Z2, utilizing the same column, means the same row, whereas an independent column for Z3. All the load transistors or pull-up transistors are located in the right hand side, like this. Coming to the left side, I have produced the functions Z4 and Z5 utilizing the same column. The load transistors are located to the left. And of course, for Z6, just like Z3, I had to use an independent column because it covers A bar, B bar, and all these things covering. So naturally, I get Z6. So you can see that the kind of approach we have used for designing this layout is not really based on a rigorous or very well-defined algorithmic approach, which what I was telling, I was trying to mention in the last class. I have given you some idea. But while managing a big VLSI structure and PLA, which will have, say, 32 inputs and a large number of output functions to be generated, in that case, we cannot handle it just like this, as we have told. You have to devise certain algorithm, and accordingly you have to develop certain software or computer program so that this is done automatically. What is available actually to an user in industry who fabricates PLA? Such arrays are available. Maybe an array of 16 inputs, that means 32 columns in a case of regular structure, and a number of outputs. There may be some quite a good amount of redundancy, and they may be personalized. This is what is known in the language of VLSI, we call it personalized. Personalized means out of that available master slice chip, we can generate any function, any set of functions, according, of course, within the limit given, and you just go on designing your masks for contact holes and metallizations so that the transistors are properly connected in the proper nodes. And that's for the regular structure. Whatever I said is for regular structure. It's very simple. But in this case, as I've already mentioned, that it is not a very good design. But whenever you are wanting an application-specific PLA, a PLA which should be very, very compact and application-specific, In that case also, algorithmic some software is available, where of course normally you have to start the fabrication from the very beginning. You cannot have any dedicated master slice kind of thing for that. You have seen already, you can have A, B, C, this, no, various kinds of possibilities are there. Therefore, you cannot have a fixed fabrication up to a certain stage. In regular PLA, you can fabricate the master slices just prior to the contact holes, contact hole etching. Thereafter, the contact hole etching, metallization, and interconnect patterning, that you do separately. But otherwise, the master slices are prefabricated, which is done in gate arrays also. So, you see the regular PLA, some advantages there, it will be very low cost that way, but you cannot gain everything, because if you cannot get everything very good. Low cost, then high speed and low power. If you now want to get low power, high speed, low power, you have to have an application specific PLA. And in that case, naturally the fabrication cost will be much higher. So an application specific PLA will be much better for large volume applications. Please remember, in applications where you need many such VLSI chips, there such application specific approach is good. So anyway, the kind of whatever I discussed till now, it is called nothing but row folding of the PLA. In fact, I have row folded not only the AND plane, but also the OR plane, but in this case it appears as if it is the column folding of AND plane, but actually it is also the row folding, which I have already mentioned in the last class. Now come to the next one. Can I do the column folding? Can I do the column? Column folding is found that is not applicable for all kinds of PLAs. You have to check the kind of functions we are handling. For example, the example which I am now giving, where column folding is preferable. The kind of example which I will now give. Let us consider the following functions to be generated. You see that these functions I arbitrarily made. I did not bother to minimize them, so you will find there may be some, these are just arbitrarily made for examples purpose only. So I have not tried to minimize them. Just for example, for demonstration purpose. If you carefully examine this function, these 6 functions and their product terms, you will find that in this particular case there is a very common thing, and that is this, that that there are a number of products which are the totally grouped kind of thing. If, for example, the product terms like D bar E, DE bar, DEF, and say DE bar, DE bar already written, D bar, E bar, F bar. This is independent of ABC. There is no ABC in these product terms. Totally separate. Totally separate. Similarly, the other product terms like AB, ABC, BC, AC, etc., they contain only A, B, and C. So we can really group the product terms into 2 groups as before, but one group does not contain any ABC, whereas the other group does not contain any DEF, kind of thing. It is an example like this. That is why I said that it is better to combine both row folding and column folding. Here, this is an example where you will find the column folding is very beneficial. Very beneficial. Okay. So in this case, what we can do really, because the group of variable output product functions which have to be created, they do not involve any ABC. Similarly, the other group do not involve any DEF. It is not necessary to apply the inputs all from the bottom. I can apply some inputs from the bottom, whereas some other inputs, say ABC and their complements from the bottom, whereas DEF and their complements from the top. And again, we have a saving of space. This is what is called column folding. So let us see. We will not consider here any row folding, sorry, any OR plane folding, only AND plane folding. So let us, how many variables are there? You just check. Total number of variables, total number of outputs. You can check. 1, 2, 1. Let me write. You just go on drawing the various columns first, various rows first. You see that you can try to draw independently. I have some limitations here. That is why I am more or less trying to follow something other. I do not have any scope for wiping off. That is a problem. Okay, so you can try yourself separately. Is there 13 product functions? Okay, please check. And I have got 6 inputs. So as I've told you that I can put ABC in one side and DEF on the other side. So what I will be doing, I'll start from here. So one question, you see that everywhere while drawing I have shown some, in both places, this is just a non-inverting stage. and then inverter. Do you know is there any logic behind it, or it is unnecessary to show it like this? Buffering, buffer purpose. No, it's for buffering, because it's a long line. The input should have a buffer stage. For isolation come buffer stage. Therefore, this is not only is keeping the signal the same, non-inverted, but it can deliver more power, more current than the main signal. The main signal will not be disturbed. That is why it is necessary. It is basically a double stage inverter, and there is a single stage inverter. There may be a little delay, does not matter, but it provides sufficient power. You see that what is Z1? Oh, sorry, let us see. We have to now produce the different functions. Term by term. We start with A, B bar, because these are the things which are produced of A, B, C. From this line downward, all the product functions, product terms are functions of A, B, C only. How to produce A, B bar? That means somewhere here I need a somewhere a dotting is necessary, isn't it? And B bar means A, B bar is it necessary to route it again through some load transistor, the one which I showed earlier? This line, does it now, do them have to go to the left and be terminated to a load transistor? Yes or no? No, I am not saying about this line and this line. Instead of suddenly, because I want row column splitting now. This is my plan is to now split columns, not rows. What I was asking you, is it necessary to just extend it to the left and connect a load transistor? No need, because these are the input lines, poly lines for the going to the gates. It is these lines are the input which I have not shown. In fact, please remember at the input of which there is always, you can just try to do it yourself. Everywhere this thing is there. So you have produced A bar, A, B bar. Next, A bar B. It produces A bar B. Then AC. Next is AC. Sorry, I think I made a mistake. AC. This produces AC, then BC. Then AB. Then ABC. then A bar BC, A B bar C, and finally A B C bar. Okay. This polyline, you know, in the earlier case you just say this polyline goes and ends somewhere. There is nothing to, you don't have to go, it does not have to go to any other transistor because these are input line. Please remember, there is no problem here. In splitting the column, there is actually problem is much less. You don't have to provide extra transistor space, routing space of the lines, etc., so that the area will be again increased. You see that earlier cases, it appeared to be very good, but then you have to provide some extra connections, etc., for which ultimately increases the space, increase the area requirement. But that is not there. Then you come to now the other things. Say, for example, I want to produce now DF, etc. So exactly in the same way, now what I do, I connect the signals from the top. Sorry. First to produce D bar, E bar, F. Okay? Then to produce DEF. Then DE bar. And ultimately D bar E. D bar E. Okay? So you see that effectively I have now the number of rows I have kept the same. Only thing is columns, number of columns have been halved, and in doing the column folding I have gained little bit more because in this case now I don't have to provide extra routing space which was needed earlier. You remember that you have to provide extra routing space in the earlier case to provide the paths for these transistors, etc. That is not there. That's an advantage. But so far as the OR plane is concerned, you may fold it or may not fold it. But in this case, the way I have drawn, I have not tried to fold the OR plane. So do it yourself. So there are 6 functions, you draw them. Okay, and of course you have to show the transistor transistors. It is better to show them. Now what is Z1? A, B bar, A, B, C bar. A, B, C bar means A, B, C bar, this line. Then plus A, B bar, C. Plus A bar, B, C. And plus A, B, C. This is Z1. What is Z2? AB plus BC plus AC. AB plus BC plus AC. Z3 is A bar B plus AB bar. Z4 is D plus D bar. That is the exclusive of D and E. Z5 is DF and D bar F. And ultimately Z6 is ABC plus DF plus DE bar. So this completes their OR plane without any folding. Now you see that, can you fold the OR plane now? Fold the columns of the OR plane now, which I have not done here. You see that if you take Z1 from this side, there is no problem for taking Z2 from this side. Am I correct? I can arrange in such a way that I can split this column into two. One column gives you Z1, the other column gives you Z2 on the top. Is it possible or not? It is possible. Then Z3, if I take from here, there is no problem of taking Z4 from the top. But so far as Z5 and Z6, there is a problem. So far as Z5 and Z6, we will put independent columns. Whereas Z1, Z2, or in fact, what you can do, Z1 and Z3 can be the same column, and Z2 and Z4 may also be the same column. There is a separation. Huh? Similarly, yeah, Z1, Z5 also you can do. So all this, but Z6 there is a problem.
No, I'm saying Z1, Z2, Z3.
Z1, Z2, Z3 is the same column. You are trying to have split of 3.
Yes.
Well, then taking out will be difficult. You have to take output from the end, isn't it? You just try to see that in the earlier example. You have to take the outputs from the two extremes now, either from this side or this side. You are suggesting that we can have 3 split of 3 columns, then output has to be taken from the center, or it is a difficult thing, which is to be avoided. By splitting, we don't mean split into 3, but just split into 2 halves. 2. Folding, that is why it is called being folded. That means you are just trying to fold it like this, okay, into 2 portions. If necessary, you can think of, but then in that case, it will be very irregular kind of structure. You see that PLA is a regular structure. We should not do anything which affects the regularity of PLA, which is very important in the design. VLSI design, if we can make it as regular as possible, design cost will be very much minimized. Overall design cost. Therefore, splitting into 3 is normally not conceived, but somebody can easily do it because in the futuristic ideas, If somebody has, he can do that. But otherwise, it is normally not done. So you see that I have given you some examples in the class. I have worked out some examples in the class which exhibit the usefulness of row folding as well as column folding for both the AND planes and OR planes. So I have done either or, not AND or. But it is possible now, if you like, to combine both AND folding and both row folding and column folding for both the planes simultaneously, if you want to have the maximum utilization of space, most efficient PLA. Okay? It is possible. For both the examples, whatever I have given, you can try to implement not only alone and row folding or alone or column folding, but the row folding and column folding combined for both A planes and both AND planes and OR planes. It is possible. And that will be the most optimum PLA, most minimized PLA. And that is the target. Normally for a good PLA design, that will be the ultimate target. Okay, with this I will stop today. But you please note down, before I go, you just take a